All right, friends, we are on the third video of chapter 1. In this one, we're going to be looking at matter, okay, and we'll hit that definition of what matter is, and we'll look at different composition of matter. Here we go. Here is that definition, okay? It's usually the first thing you learn in chemistry. Matter is anything that occupies space and has mass, okay? So it takes up space, has mass, and that's matter, and that's what we'll be studying here. Everything around you, your textbook, your desk, your chair, your body, all composed of matter. We will classify matter two ways, okay? First is by its state, and that's its physical form. We'll look at that the last video of this chapter. And then in this one, we're going to be looking at its composition. What makes it up and how can we separate it based on composition? All right, let's look at this image here. So if you want to look carefully at this, you can see matter up at top. Okay, and matter can be divided into either a pure substance or a mixture. And the way to see the difference is its composition variable? Can it change? And if the answer is yes, you have a mixture. If it's no, it's always the same as it is, okay, that would be a pure substance. Now, a pure substance can also be broken down into an element or a compound. Now, a compound can be broken down further to an element. So if it's the simplest that it can be, then you'd be an element, okay? And if elements make up, okay, atoms of two or more elements can make up a compound. All right, so that's that side. We'll talk about that a little bit more details, but let's go to the other side, the mixture side. Now, if it's uniform mixture, okay, it would be a homogeneous or homogeneous. Sometimes it's pronounced either way. Usually I say homogeneous. Some students say homogeneous. Homogeneous or homogeneous mixtures also are called solutions. So we'll be talking a lot about solutions later on in the book as well. If it is uniform throughout, homogeneous. If it's not, it would be considered a heterogeneous. Now, sometimes it's hard to tell. Is it a homogeneous or a heterogeneous? Looking at the pictures here, though, you can kind of see the difference. All right. The homogeneous mixture has several things in it. You can see some water. This is tea with sugar. You can see some water. You can see some sugar molecules. Okay, those are some of the big ones. There's other molecules from the tea. Okay, maybe it's lemon tea. You have some citric acid in there. So you have lots of things in there. It's all mixed completely throughout, pretty uniform. And if you look at the tea, you can't see, oh, this one spot has got, you know, something in it and this spot doesn't have it. Or the color's the same. It looks very uniform. That would be the homogeneous. Heterogeneous, you can see where it's different throughout. Now, wet sand, okay, you have water, and then you have water kind of mixed with some sand down below. You can see two distinct layers there in that image, so that would be considered a heterogeneous mixture. Sometimes it's a little bit difficult and to classify the difference. So the example that I think of would be blood. Okay, so sometimes you can argue both ways. If you just look at a drop of blood, it's red, it looks the same throughout. But if you look at blood under a microscope, you can see maybe some red blood cells, some white blood cells, some other things in there, the plasma. So you could see different layers in different parts, and it might not be all uniform throughout. So blood, you could say under a microscope would be heterogeneous. If you're just looking at it to the naked eye, it looks homogeneous. So there's some area I would say that you could definitely argue both ways, but a lot of times we'll try to give you examples that are definitely heterogeneous or homogeneous. If you have filtered orange juice, okay, the pulp is removed, that would, you would say, would be homogeneous. But if you have orange juice with the pulp, okay, that's not going to be all mixed throughout evenly, that would be heterogeneous. All right, switching to the other side, the pure substances, elements, and compounds, we mentioned that the compound contains a molecule with two or more elements. Elements, those are what you find on the periodic table. There's over 100 different elements that you have on the periodic table. And elements can be atoms of that element, or you could also have molecules of that atom, of that element, sorry. Different there, okay, so you see helium in that. There's just singular balls, okay, that are representing an atom from helium. Now, if you had oxygen in that sample, well, oxygen doesn't like to just stay as one oxygen atom. So natural state of oxygen would be O2. And you've heard of that. What that means is there's two oxygen atoms bound together. Okay, there's a covalent bond between the two of them. And so it is considered an element, okay? Oxygen is an element, but there is 2 atoms of oxygen together, so it would be a molecule of that element. So things to check here, compound, those ones, okay, they all have the unique same formula. So if you have water, it's always going to be H2O, and you can see in that pure water, you have hydrogen and oxygen making up water. Now if you have some H2O and some OHs, okay, that would be something else. That would not be just pure water, okay, you might have water and a base there, okay, so then you have a solution. The other thing that students sometimes get confused at is sometimes they get compounds confused with homogeneous mixtures, okay. The example of water is a great one, okay, so we're going to go with water. If you have pure water, you just have H2O. Now this water looks like it's in a drinking glass, and so sometimes that gets a little confusing because I would say that if you have tap water, you don't just have pure H2O. How do I know that? If you drink water at one place at your house, you're used to the water at your house, you go somewhere else, drink the water there, sometimes it tastes a little funny to you, right? Or sometimes when you're trying to wash your hair, just the way that the soap comes out of your hair is a little different, and that's because the water is not just pure H2O, it's usually a mixture, okay, and hopefully it's a homogeneous mixture. It would be really bad if your tap water was a heterogeneous mixture, but it's a homogeneous mixture. There's other things in there. You might have some things to kill bacteria in your water, so you might have some like chlorides, some sodium, some ions. Sometimes if you have bad pipes, you know, some of the metals might leach out. So you might have other things in there in your water except for just pure H2O. So tap water, I would say homogeneous mixture. You will probably get some worksheet, other questions that we'll ask you to clarify and go through. Let's just look at some pictures here as well. You can see the top one. There's 2 different ways to represent elements. Like we said, elements would be pure substances and then elements, okay? They're just one thing from the periodic table. It could be their atom, okay, so it's just singular atoms, or molecules. And notice that the molecules here are both purple, okay? They're the same element, and that would be a molecule of an element. Go down to the bottom, okay? Compound, also pure substance, okay? Element, just one type of element, atoms or molecules of one element, versus compound. Now you can see some green and pink balls here, all right? So this would be 2 different elements that make up the compound. All of the different molecules in that compound are the same, okay? It's all the same thing in that box. That's why it's a pure substance and not a mixture. So look at the different varieties of mixtures you could get. You could get a mixture of atoms that are, of elements that are atoms, okay? So that would be the green and the orange there. You could get a mixture of elements, okay? One could be an atom and one could be a molecule of an atom. Or you could get a mixture of molecules, okay? So different molecules of an element, okay? That would be the next box over. And then the last one, you have a compound and an element mixed together. And you could change the composition, okay? So you could take it and have more orange and less green balls, okay? And its composition can still change around just by how much you add of the different components that make up your mixture. Hopefully those images kind of help cement those definitions for you. Let's just see if we can answer some questions on. Here's a mixture. Let's talk about what makes up this mixture. All right, so first off, you can see 3 different things. Okay, one of them is a compound, 2 of them are elements. Can you figure out which one's which? The elements would be either singular balls, okay, that represents an atom from one element, or you could have, okay, 2 of the balls that are the same color, this dark purple here, they're the same color, so they're the same element. This would be a molecule of that element. And then the last one, here's your compound. You have green and the purple, okay, so that's 2 different elements that make up this compound. So this is a mixture. We can change its composition. This one looks like it's in the gas phase, so it's probably filling the whole area, and it would be a homogeneous mixture. All right, when we look at chemistry, just to go through a couple different ways of representing things, we'll get used to it as we continue on, but you can write a formula out. This would be called a molecular formula. This is the exact number of atoms of each element that make up the molecule. Okay, so a molecule has at least 2 or more atoms. Okay, and like we said, the molecule can have atoms of the same element, Okay, that would be called an element, or atoms of a different, that would be called a compound. For example, we're using water here. You can see hydrogen and oxygen. There's a subscript after the hydrogen, so that says that this formula here for water has 2 hydrogen and 1 oxygen atom. Another way to represent that is to show the bonds that are taking place. So the oxygen's in the middle, has hydrogen bonded to it. And this is a covalent bond where we're sharing electrons, and so you can see 2 dots on either side of the oxygen from where those electrons are being shared with the hydrogen. These are now structural formulas. Okay, it's showing a little bit of how things are attached to each other. Are the 2 hydrogens attached and then the oxygen on the end? No, this one has oxygen in the middle, 2 hydrogens on the side. Now, the dots represented the 2 electrons that are being shared. Oftentimes, just for speed's sake, we just make a dash right there, and that represents the bond as well. Now, you can also look at a ball and stick model. Okay, so instead of having oxygen and hydrogen written out with their letters, you can have it represented by balls, and then the sticks represent the bond taking place. These will show you a little bit more detail as well about the shape of the molecule. And you have a space-filling one that also takes into account not only the shape, but how things are filled up. So if, you know, the approximate size of things, what it would look like. So as we continue on, we'll get more practice with this, and we'll continue with using all these different types of formula. Just looking also at chemical formula a little bit more. Like we said, they will tell you the type and the number of atoms in a molecule, or it will tell you the ratio. Okay, so first example here is sucrose, C12H22O11. It has a parentheses around it and an S. That stands that it's a solid. Okay, so sucrose is the name. You can see, if you look here, you can see all the oxygens written out. You can see at least most of the hydrogens written out. You do not see the carbons there. When you look at the structural formula, one of the shortcuts that they use in organic chemistry is to leave out drawing all the carbons, because we have to make quite a few of them. And so we'll get into figuring out how to do these line drawings and where those carbons are later on as we go. So we'll get into that one. The next one is methanol. Methanol is CH3OH. Total of 4 hydrogens, but you can see it's written out CH3 and OH. That's because the OH is a group coming off of it, so it kind of keeps that separated. You can see that there are several methanol molecules here. 1, 2, 3, 4, 5, 6. I think 6 of them there. You can see a couple waters in there as well. And so this is showing kind of their shape, the line drawings here, or structural drawings showing their shape a little bit, and some of the interactions between the molecules of methanol and methanol and water, and how they interact. Again, as we go on in chemistry, a lot of this will come into you, and we'll talk about this in more detail. The last one, the formula says NaCl, and it's a solid. This is your table salt. This is sodium chloride. Now, when you see NaCl, you think, oh, there's 1 sodium and 1 chloride. And that's true, but you look at that picture, there's a lot more sodium and chloride atoms involved here. So this one would be considered an ionic compound. We'll talk more about that as well. But we have sodium and chloride, and this is the ratio of sodium to chloride. So for every 1 sodium, there's 1 chloride. And so you can see that depicted in that crystal structure there for sodium chloride. All right, lastly, visualizing chemistry. You see ice melting. Before this class, you just saw ice going from a solid to a liquid. Now after this class, and during this class, I want you to think, okay, when it's going from a solid to a liquid, what's really going on here? What are the changes in interaction between what's holding the water and water molecules together in the solid, and how is that changing and adjusting as heat is being added and this is turning into a liquid? So that is kind of our goal. Whenever you see something, I want you to start thinking and visualizing as a chemist would. And we'll do that as we continue on.